Students, welcome back to the part 2 of lecture number 8. So, we have been discussing about gradient descent algorithm in machine learning, right? And I hope you understood the meaning of this curve. So, idea is to go down the hill when you are talking about gradient descent method and find the best direction in which you can easily reach the global minimum. That is the idea, right, in this technique, and explain you different steps. Okay, let me tell you again. So, first we go to the top of the hill. That means we start with some random guess for the model parameters. Every model has some free parameters, right, which are going to optimize. So, therefore, you start with some random guess of the model parameter, and then you feel actually the slope. Feel the slope means you look around, see which direction the ground is sloping down, right. There are several directions ground may slope down, right. That is what is you calculate the slopes or the gradient in different directions, and then from that gradients you find out the steepest way downhill. But after that you take a step down, move the direction where the slope is the steepest. Obviously, bigger the slope, bigger step you can take, or larger step you can take, right. That is what you do. So, how it is done? Fundamentally, basically it is nothing but an optimization technique. You understand that we optimize to do what? Optimize to minimize the error or the cost functions of a model, and by how we do, we iteratively adjust the model parameters. There are model parameters, like in case of regressions, linear regression, there is only one model parameter, y is equal to ax, okay, or y is equal to mx plus c. There are two model parameters, m is the slope and c is your intercept on the y axis. If you have a nonlinear model, you have many model parameters. So, you iteratively adjust these model parameters to achieve reduction in the difference between the predicted value and the actual value, or they improve the model's performance simply by minimizing the error. So, that is what is the idea. It is basically optimization technique, remember that. Well, let me tell you this again. Let us say this is your error or cost. Okay. We always write cost in machine learning, it can be error also, and these are your weights, or weights means your model parameters, correct. So, you can see that this is your curve, right, and this is your minimum cost, minimum error. So, now what you do? You can always take initial weight, put it here and slowly move slowly to reach this point, correct. In order to do that, you have to choose the steepest path, and to do the steepest path you must know the gradient. That is why you are at the top of the hill, you look around, find the slope and move in the direction of the steepest slope. That is what is called the gradient descent method, right. So, now I am talking about you cost function. Okay, let me explain to you what is a cost function. Cost function is nothing but the one which quantifies the error or the loss of model prediction compared to the true values. Whenever you are predicting something, you will be comparing that prediction with your actual values, right. So, difference between this predicted value and the actual value is what is known as your loss or error, okay. And the cost function actually tells you, the quantifies you the error, right. So, simple cost function is the mean square error, right, when you are calculating, and there are many such errors actually, by many ways of calculating error, but mean square error is what is the easiest way to calculate error, right. And you know what is it? It is basically root over y predicted minus y actual whole square, right. That is what is called mean square error, okay. Many of you use mean square error, mean absolute error, right. So, mean square error is that. So, you always, that is your cost function, okay. So, it quantifies how much is the error model prediction vis-a-vis true values. So, there are different kinds of error function I told you, right. The easiest one is the mean square error. It is commonly used in regression problem. That is what we will discuss in today's lecture also. It is commonly used in your regression problem. And what is that it do? It calculates two important thing. It calculates the square of the difference between the predicted value and the actual value, and then it takes the average. So, basically it's, if you want to write in mathematical form, it is 1 by n and then I goes to 1 to n, okay, root over y I, Okay. This is predicted minus yi actual square. That is what it is, correct. And you can see we are basically averaging out for all the n values. You can also have other things like cross entropy, often employed in classification tasks. Okay, I will discuss these aspects in case of descent trees. It measures the performance of a classification model whose output is probability values between 0 and 1, like in Bayesian classification problem. That is what you do. You can also use hinge loss. This is used in maximum margin classifications, is used in case of support vector machines. I discussed it. We will discuss it when you talk about support vector machines. Right now, for you to understand, you can focus on mean square error. That is the error functions. Okay. Now, what are the factors actually? Okay, we will come back to this. Let me go back to the board and discuss you that basic technique of that. Okay. So, first of all, let me also explain few other aspects. So, as you can see that when you are going down the hill, let us say you are going down the hill, this is what is your hill, okay, and this is your minimum point or minimum loss point. You are going down the hill, this is your steepest path, right. And I told you, right, you can always go like this also, you can always go like even this also, you can always go like this also, but none of these has the highest slope. This is the path 1 has the steepest slope. Okay. Now, the question is, if you want to move along the path 1, that is steepest slope, how much step you will take? Will you go one step, just like jump from here to there, or will you take a small steps and go like this, or will you take intermediate steps? That is what is called learning rate in case of machine learning, the step size, that is what is called a learning rate. So, first you select the steepest path and then you select the step when you move along the path. The step can be large or small, correct. That is what can happen. So, let us talk about what will happen when you take what is the optimum learning rate. Okay. The gradient actually is guiding, this gradient when you calculate is guiding you what? It is basically gradients are guiding you the ensuring convergence towards this point, ensuring reaching this point here. Okay. That is what is the gradient does, reaching this point, right. But how to reach that point? Okay. That is what is important. The gradual steps used in this descent, the steps which is basically is known as a learning rate. So, that means the gradual steps used to reach the minimum of cost function or loss function is what is called as the learning rate, gradual steps used. Okay. Obviously, you will take gradual step, you will never take a long step. What will happen? Let me also explain to you. So, learning rate is very important hyperparameter in machine learning, very important hyperparameter. Remember this. This is very important hyperparameter. Many hyperparameters we will discuss. This is one of the hyperparameters, very important hyperparameter. And basically, it controls how big or small steps should one be taking when going down. Okay, that is what is very important. Okay, that is the very important. You have to understand that. So, let me explain to you these aspects. If the rate is very small, okay, very small like this. Let us say I am coming down from here, I have taken a very small step, correct. If the rate is too small, what will happen? Algorithm will take tiny steps, very small steps. Remember this, it is taking this small step, let us say this is taking delta s, very small step. So, when it takes very small step, it will take a very long time to reach this level. So, that means first of all it will be computationally also intensive, because you are going to follow many steps, and also it will be taking more time. That is the key point when you use very small learning rate. So, small learning rate, this is the problem you will face always. Okay. So, therefore, it is significantly to be increased, so that computational cost can be reduced for large data sets. That is what is very important. But on the other hand, if you use a large steps, large learning rate, what will happen? Large. You can clearly see here, no, I have taken a large, I am jumping over. From here I jump here, from there I jump here, from there I jump here and reach the minimum points. What will happen here? Algorithm may take a huge steps, okay, and it may actually overshoot the minimum point. Minimum point is here, you can see here, minimum point is here, this is what the minimum point, but it has overshoot the minimum cost function without even settling, correct. So, this is the key challenge. If you use a very large step, you may reach fast, but you may overshoot this point. You may not reach that error point at all, you will overshoot it or reach after that or before that. That is the key challenge. Therefore, neither small nor large is a good learning rate. You have to use the optimum learning rate. This becomes a hyperparameter. That is what I say, this becomes a hyperparameter, and that you need to tune in many of the machine learning models. This becomes a very big important hyperparameter that you need to look. Okay. So, to address this problem, some techniques that can be used. Okay. First is obviously weight regularization. Weight regularization, that is very important to address this large step or small step problem. Okay. The initiation of the weights can be adjusted. Initiation of the weights, whatever initial guess you are doing, that initiation of the weights can be adjusted. So, therefore, they are in the approximate range. This is easily very normally done in case of the Newton adaptations like numerical tools, where you have to really adjust the initial weight so that you reach your minimum loss point, correct. And you can use always rectified linear units and other things also, correct. That is the very important aspect, you have to understand that. Or you can use gradient clipping, or you can use batch normalization. These three techniques which are used for the optimum step size. What is gradient clipping? Basically restrict the gradient to be a predefined range. You restrict the gradient to be a predefined range. Okay. When every time you are moving, you are calculating the gradient, right, slope. So, you can always say my gradient will be between these and these values, that to select, and in order to do that you select your step size. Okay. So, that is what is called a gradient clipping method. Or you can use batch normalization method. What is that? It can also help to address the problem simply by normalizing the input of each layer, or to prevent this activation function from saturating, correct. So, what does it says? That it can be normalizing the input of each layer, each step you are doing, input is normalized, okay, because you start with this input each here, then this becomes next to the next one, that inputs can be normalized. That is what is called a batch normalization. So, either you can regularize the weights of these functions, or you can use gradient clipping or a batch normalization to decide which is the optimum learning rate. That is how we can tune the hyperparameter. Okay, you must be hearing these words a lot, hyperparameter tuning. Now you understand that this learning rate is tuned to reach this point the best possible way, right. So, after explaining this, let me now talk about the mathematical parts of the gradient, okay, gradient problems. So, I just erase this part. I hope you could understand the learning rate, because this is also will be used in some other machine learning models. So, let us go back to I will use only regression, remember this, because you have learned regression, and I will use regression to explain the mathematical part of that. So, let us consider a linear regression model, okay, that is also the easiest model in machine learning, linear regression model, okay, with a single input feature x input or variable is your x, and output or we call label is y. You know that, right? This is a linear equation between x and y. So, y is equal to mx plus c. This is the standard linear equation which you are trying to fit. So, what is the mean square error? In this case, it's obviously is like that. Okay, let me write this. Instead of y is equal to mx plus c, I write y is equal to wx plus b. My parameters are in this model at w and b, which you are going to optimize to find the best fit. So, a mean square error, which will be a function of w and b, is basically equal to 1 by n. I have already written 1 by n, n goes to I goes to 1 to n, and this is yb minus y square, right. That is what is mean square error is. Okay. So, you can clearly see that. So, here yb is what? Yb is x into w plus b, right. So, this is yp, not b. So, yp predicted value, and this is the actual value ya. So, yp, this is the predicted value by your model, that is x into w plus b, and y a is the actual value. Okay. That is, you understand, this is the mean square error in a case of a linear regression model with two parameters w and b. Linear model will be like a straight line equation, and straight line equation is this, where w is your slope and b is your intercept on the y axis. So, when you fit your data, fit your line basically from your data sets, whatever, you basically optimize the value of w and b to get the best fit. And once you have a best fit, then you can predict for any new value of x, what is the value of y. That is what machine learning does. So, now this is your predicted value, and this is your actual value. You will be comparing with that difference between this and take a square for each step, sum it over, divide by the number of steps. It is what is called the average value or average MSE, right, mean square error. So, now the question is this: if you want to optimize this model, so you have to optimize this model parameters, right, w and b. You want to optimize the parameters, you can always calculate the gradient. The gradient with respect to w is what? Gradient with respect to w is what? We can always write down del j wb divided by del w, right. So, what is this? That is equal to del w into 1 by n, sum it over I going to 1 to n yp minus ya whole square. Am I clear? That is what it is, your gradient with respect to w. There will be gradient with respect to b also. Am I clear? So, that is what is your gradient with respect to b. Now, what you do in this case, in order to get this gradient value, so we substitute this yp substitute with this x into w minus b, right. So, you can clearly see this slope will be what? This slope will be, this slope is 2 by n, this square will come down. So, this will be 2 by n multiplied by this summation I into 1 to n yp minus ya, right, into del w multiplied by x w plus b. Okay. That is what will be there. Am I clear? Because this guy, oh sorry, minus ya. If I can actually write down that for your to help you out, you can do the mathematics also yourself. 1 by n, this I goes to 1 to n, and yp is, I can write down, yp is what? Yp is this. We didn't write because then the square term will not be, yp is into x w plus b minus ya whole square, correct. That is what it is. So, now from this we can easily get that. From the square, this 2 will come out, this will be 2 by n, and then this will remain same when you differentiate. Further you differentiate this. Am I clear? So, now if I have to write down the final answer, so I erase this part, just wanted to show you how it is to be done. What is the final value? Final value of this is 2 by n, sum it over I1 to n yp minus ya into x. Obviously, because these two guys are constant for w, b and ya. So, the only x into w differentiated, that is your first gradient respect to respect to w. Okay? You understand that? So, now this is what you calculate. It is very easy in linear regression model. This is what you calculate the gradient with respect to w. Remember, this depends on x, right? Both ya also has x, you can yp also has x, yp has also x, and x is there already. So, it depends on the x, depends on the coordinated x, remember this. Okay? So, that is how actually in linear regression model you can minimize this error, and remember this slope is related to minimization of the MSE. This slope is related to minimization of MSE. If you want to minimize this mean square error, you have to put this slope to 0. Am I clear? That is why you do in minimization functions. But since this is from a data science, you are handling a lot of data, you cannot do this, you have to use data to do that. That is why you always figure out how to calculate the slope, right. So, I hope you understood that, right. You understood how to calculate the slope. Now, you always understand that once the gradients are calculated, we can update these parameters both w as well as b, okay, and you have to update that each step, and so that you can minimize the loss functions. So, there are two ways of updating that, it. One is by if we take a positive gradient, okay. Let us do that actually. If you take a positive gradient, how it will look like if you take a negative gradient. So, I remove this part and show you one by one what can happen if I take a positive gradient or negative gradient, right. So, let us take you have a curve like this, which I have drawn earlier, and you are going in a positive gradient, moving like this, correct. You understand the gradient, right. Gradient is what? This is y, this is x, okay. So, basically m is nothing but a tan theta. Am I clear? So, if I have a curve like this is what is your slope here at this point, correct. This slope is negative, right, because tan theta is negative. But if I have a curve like this exactly other way, okay, if I take a slope of that, this slope is positive, right. Tan theta is this divided by this. So, that is why I can have both the situations, I can have positive slope or negative slope. So, this is what is your okay positive gradient, this is for positive gradient, you can clearly see. So, there w will be equal to w minus gamma into dw by dj wp divided by dw, okay. This is your initial value, w0 is initial guess, right, initial guess, and gamma is your learning rate of step size. What you are doing? Simply you are adjusting the value of w. This is your new w. New w is nothing but the old w, okay. Initial guess or old values, right, minus the step size into multiplied by your slope, this guy. That is how we can keep on reduce your the step size, your learning rate, okay. That is what you can reduce your step size, how it will go down, I remember, I hope I remember, right? That's a step size. So, this is how it allows you to calculate your step size. Okay, if you know the learning rate, then you can reduce the step size in a very systematic manner. So, that is for the positive gradient. What will happen if you take a negative gradient? If you take a negative gradient, what will happen? Very simple. So, for negative gradient, it is not very simple. The negative subtracting negative gradient, this will be plus. So, if you have a, so let me do it here itself for your purpose, so that you can compare yourself. If I have a negative gradient, okay, and I am coming down here, since getting a negative, so it will be W new will be W old plus gamma multiplied by dj WB by dW. Okay. So, this is for your gradient positive and this is for negative gradient. This is how we can basically go step by step. This modeling you need to do very well. I hope this is very clear to you how it is going to work. Okay. First is to calculate the slope, then using the what is that called, learning rate, you can calculate other things. So, which are the factors which control this gradient descent efficiency? First is the differentiability, mathematically, right. Gradient descent requires the cost function to be differentiable. If it is not differentiable, you cannot do anything. There are many functions which are continuous, but not differentiable. So, you can see how much mathematics comes into picture. Differentiable function allows you to compute the gradient at any step, and that is what indicates the direction of the steepest slope. Second important things, so that is basically nothing but a first derivative, first order derivative, which you call f prime x. Now, second factor is important function, the convexity. Cost function must ideally be convex to ensure the gradient descent can reliably found the Gowal minimum. And how do you measure the convexity? Simply by second derivative. It must be non-negative, right. That is the condition of minimization. For minimization, first you calculate the first derivative, put it 0, then calculate the second derivative for the value of x for which double derivative is non-negative, then only it is a minimum, right. That is what exactly it is telling. This is nothing new. Okay. So, hope I have made you clear. So, now I just wanted to just introduce the concept of what is called ensemble learning, which you started together today. Okay. What is ensemble learning? Okay, you know, ensemble learning is basically committee based learning. Very interesting, right? Very committee based learning. What is done here? In which a committee has many members, right? And each member actually is what does do? Each member is an individual learner. So, you have a committee, or you have a community also, you can say. Committee is very easy to say. Committee has many members, each member is an active learner. And so, what will happen? And it has a learning algorithm. Algorithm can be many things, can be one algorithm can be simply regression, other can be descent tree, some other can be SVM. So, each person learns one learning methods. And prediction is basically what? Prediction is basically ensemble learning is basically given by the weightage average or weighted things of the best learners. So, each best learner is learning from its algorithm. When you basically put together, take a weighted average of that, that is what is called ensemble. That is why it is called ensemble learning. ADA boost is a part of ensemble learning, many of you. Gradient boost is a part of ensemble learning. That is what we have to discuss about these aspects. So, now if all the members learn, base learner is same, that is called homogeneous learning. If the learners are learning different algorithms, it is called heterogeneous learning. So, you can have different kinds of situation. So, what you understand is very simple, right? That is how the new algorithms comes to picture. First thing you are understanding that in case of ensemble learning, you have a committee, and the committee has many learners, each of them learning with a very base algorithm, okay, base learning algorithm, and prediction is given by weighted average of the each of these learners experience. That is what is called a ensemble learning. Now, how it is done mathematically, how we can treat it and how we can actually understand it, we will discuss in the next class in more details, but you can always read through. There are a lot of literature available on books as well as on internets. So, two important learning methods which we are going to discuss is basically ADBoost or AdaBoost classification, other one is we are going to discuss is gradient boost. I already discussed about gradient, so we will talk about gradient boostings in the next 1 or 2 lectures, all these things will be discussed. Okay, let me stop here. Thank you.